Hello, my name is Dave Shippey, and I'm here at the Cold Climate Housing Research Center in Fairbanks, Alaska. And today we're going to talk about building a remote wall assembly. And remote stands for Residential Exterior Membrane Outside Insulation Technique. And what that means for us is we're going to take the vapor barrier and insulation that's traditionally in the wall cavity, and we're going to bring it to the outside of the structure. When we do that, we're going to change the materials we use. We're not going to use polyethylene and fiberglass. We're going to use bituthane and some drain wrap, which are air barriers and moisture barriers. And for the insulation, we're going to use expanded polystyrene foam. Now, when we bring those systems to the outside of the building, it's going to do a couple of things for us. We're going to be able to have a more continuous air moisture barrier on the outside. It's not going to have penetrations for outlets and switches and such. And it'll be continuous from the roof all the way down to the footer. It won't have to go from floor to floor, and have any intermediate breaks in it. It'll be one continuous envelope. And we'll do the same with the expanded polystyrene. It'll be one continuous covering of polystyrene insulation, very windproof, and the polystyrene doesn't suffer from R-value decay with decrease in outside air temperature as some other insulations do. We have a little mock-up here, visual aids, and it's the framing side to side is, of course, is to scale, but of course it's not scale top to bottom. If you have an older house that has 2x4 walls, there's not much insulation in the walls. If the insulation was done very well, the insulation will be fluffed out nicely, it'll be cut accurately. But even if the insulating contractor did a good job, there's still not much there. And where the corners are, where there's extra wood, that squeezes down the insulation and reduces its R value, and it displaces the insulation. The more wood that you have, these wood members are conductive, and they conduct heat directly from the inside to the outside. This fiberglass insulation is nicely done. It's cut to the proper width. It's fluffed in there, full width, it fills the entire cavity. This piece of insulation, if your insulation contractor had to cut it a little too wide, stuffed it in anyway, looked good from the inside, but on the back it's puckered. And that will create a cavity where a convective air cycle can basically operate as a heat pump to take warm air from the warm side and transfer it to the cold side in a continuous cycle. And this will show up as an area of high heat loss on a thermal imaging camera. Of course, the other deficiency could be the insulation. It looked okay, but it was a little short, but they put it in anyway. This will show up on a thermal imaging camera as a very wide stud, sort of extra heat loss in that area. And when you're putting insulation in an 8-foot wall and you're looking up, it looks tight, but maybe it was a little loose, and then over time it can settle a little bit. That'll show up as an area of extra high heat loss as well. Other areas of deficiencies in a wall like this for both insulation and vapor barrier are outlets. You put an outlet and switches in the exterior walls, and they displace insulation. Behind the outlet, you might only get an inch of insulation. And then this type of outlet, or any outlet, needs to have a diaper around it, a plastic bag with sort of flanges on it that can be vapor barriered with the interior wall. If that hasn't been done, in a lot of older houses it hasn't been, and air from outside will leak in through the outlets. The double top plate in a house is solid wood, so there's no insulation between the sheetrock and the exterior. And if the insulation in the ceiling is not cut really well, it's bunched up in there, this will be a real cold spot in the house, and sometimes there'll even be discoloration on it, or discoloration on the sheetrock screws. And that's because they've gotten so cold that the moisture in the house has actually begun to condense on those areas. And that's a telltale sign that you've got a lot of heat loss in this area. Insulating the rim joist area of a floor system can be difficult to do with fiberglass. Cutting the little pieces and then trying to vapor barrier between the floor joists is, especially the flange style floor joists, is very, very difficult. Very difficult to cure all the air leaks that can happen between the top of the mud sill and the bottom of the rim joist, and underneath the floor deck. There's another gap between the floor deck and the bottom plate that's a potential leak. And because the vapor barrier has to stop and skip, go from floor to floor, it's a lot of tedious work that's very difficult to achieve a good quality outcome. The remote system is going to help us cure a lot of these problems, because the air vapor barrier is going to go on the outside, and it's going to be continuous all the way from the rafters, all the way down past the rim joist, all the way to the footer. So it's going to help stop all of these potential air leaks in. The other thing, when we move the insulation to the outside, we're going to cure a lot of the thermal conduction problems that we have with having to skip from wall assembly to floor assembly. The insulation will be continuous and unbroken all the way down with no interruptions and no conduction from the framing members directly to the outside. We've looked at a lot of the deficiencies in a sort of a regular wall assembly and talked a little bit about how the remote system is going to help us out with those deficiencies. Here we have a wall that we've covered in bituthane. There's other products that you can use. We've used some drain wrap. It's a Tyvek product with crinkles in it, but it's applied in the same manner. It's applied from the top all the way to the bottom. And everything is applied shingle style. Start at the bottom and come up, and every successive layer laps over. The windows are flashed shingle style, starting at the bottom, sides, and top. And once you're done putting your air vapor barrier on the outside of a remote structure, you should be able to take a hose and spray this anywhere, and none of your wood should ever get wet. It should be completely free, completely resistant to bulk water. Once you have your continuous air vapor barrier on the outside, then it's time to put the insulation on. How much we put on is critical. It matters. We don't want this plane of the wall assembly to reach dew point. We don't want the sheathing to reach dew point. We don't want the framing to reach dew point. So we have to keep it warm enough to not reach dew point. And the way to do that is to put at least a ratio of 2/3 on the outside of it versus 1/3 on the inside of it. So we have R11 on the inside in a 2x4 wall. So you double that, you get R22. So we need 4 inches of foam on the outside to get a roughly 2/3 to 1/3 ratio. And that'll keep everything on the inside above dew point. There'll be no condensation, no moisture issues, no mold issues inside your wall cavity. We've got our wall airtight, we've got it well insulated, and now we need to address the roof. In new construction, you're probably going to order a truss with an energy heel. And so directly above the wall, you'll have 18 inches of space between the top of the wall and the sheathing. And that allows you to put at least 16 inches of cellulose in the truss cavity. And that'll get you an R60 ceiling, which we recommend. If in a retrofit situation in an old house, if you do have nice tall trusses, you got a good energy heel area, and you can get R60 cellulose blown in, then that would be the most cost-effective way to increase the R value of your roof and bring it up to R60. Sometimes you're not going to be that lucky, and you're going to have a roof structure that just doesn't have the depth to add more insulation to. If you have a 2x8 roof or 2x10 roof, the most you're going to get in there is R25, R30 respectively. So then to bring that up to R60 for this video, not only are we going to remote retrofit the wall, we're going to do the roof in a remote retrofit technique as well. If you have shallow rafters, and some of the rafter space is left open for ventilation in the top, that really limits the amount of insulation that's in there. So to increase it to R60, you have two choices. You can increase its depth and come down, or increase its depth by going up. And part of the beauty of the remote situation in new construction is that you can be applying insulation to the outside while the rest of the HVAC crews and plumbers are on the inside. The same is true in a retrofit situation where if you're living in the house and you don't want to tear down the sheetrock, then the best option is to go up. So you don't have good, if your ceiling vapor barrier is suspect, maybe you've done some investigation and it's not there at all, or it's done very poorly, it's not sealed around the edges, it's not sealed around the fixtures, there's a lot of wall partitions where the vapor barrier just comes to one side of the wall and the other, but it's not really sealed to the top of the wall. There's lots of plumbing penetrations through the walls, through the vapor barrier, and there's just sort of no hope of ever really fixing the vapor barrier. And you really don't want to tear down the sheetrock in your house. Then going up is the best option, and there's a couple different ways. You could reframe it and put more fiberglass in, but we think doing the remote layers is going to be a better way to go. And what we're going to do is we're going to cut the rafter tails, cut the eaves off flush with the wall. We're going to carry our air vapor barrier up all the way over the roof and all the way down the other side of the house. It's going to make a very tight envelope, a complete air barrier over the entire house with very, very few penetrations. It's going to be very little air leakage in the house once you're done doing this. And then we're going to put insulation on the top, and we're going to use foam again. We use a higher density foam, expanded polystyrene, and how much we put on the roof is dependent on how much is already in the ceiling, because we're going to keep our 2/3, 1/3 ratio again. Our new vapor barrier is going to be here, our new air vapor barrier, so we're going to want 2/3 of the R value of our total assembly above it and 1/3 below it. And by doing that, all of the framing and everything, the sheathing, everything that's now inside that vapor barrier is going to stay above dew point. It'll never get cold enough to condense any of the moisture in the air. So the wall cavity will stay dry and there'll be no mold or moisture issues. This is Grace Ice and Water Shield. It's a peel and stick membrane. It's 30 mils thick, it's very thick. It's a slight texture on it to make it a little safer to walk on. It's very typical, used in roofing applications. typically used on the edges to prevent ice damming. We're going to use it over the entire roof. It's waterproof, windproof, has a very low perm rating, and we basically peel it, stick it on the roof, and we'd bring it down shingle style over whatever we've used for the air water barrier on the walls. And everything done shingle style, any water that gets on here anywhere on the building will run down and into the ground at the footer. At the research center, our building has 6 inches of foam on it. The research center is built in a very low-lying area and has very, very cold temperatures. It's more money, but the investment is well worth it to put 6 inches of foam. 6 inches of foam on the side of the building. What we've done is we've run it up to the depths of the foam insulation we're going to put on the roof. Now, in this case, we probably have R20 or so in the roof already. So if we double that, that's R40. So we're going to need 8+ inches of foam. So we have three 3-inch thick layers of foam, and that's going to give us 2/3, 1/3 ratio with our R values. 2/3 of the R value of the whole roof assembly is on the outside of the vapor barrier, and only 1/3 of the R value is on the inside of the vapor barrier. And with that ratio, we're confident that everything inside the vapor barrier is going to stay above dew point. It's going to stay warm enough that there'll be no condensing in the roof cavity, no condensing on any of the framing members, and it'll be a very dry, mold-free roof assembly. Attaching the foam, we use screws. If you are going to put a stucco finish on the foam, which we have at Cold Climate, we have a synthetic stucco, very flexible, very tough, very maintenance-free. We have that on the outside of the building. And when you put stucco on, you use a plastic washer like this. And they're available at the local supply store, and very long screws. And for 6 inches of foam, we use an 8-inch screw. And the washer goes on the screw and holds the foam onto the building. The washer has very high wind load. 16 inches on a grid is typical. For the roof, as the foam gets thicker and thicker, longer and longer screws. And these screws are available. We have screws from 6 inches up to 16 inches and larger. You can get them any size. We like the ones with the Phillips head. These are a number 3 bit, a little larger than a standard Phillips bit. But they're very low profile, and any other surface that you might want to put on top, it doesn't have to go over a big bump. It's a nice small profile. In this situation, we had 2x8 rafters and about R20 insulation. If you have thicker rafters, say 2x10, you might have as high as R30. To get the 2/3, 1/3, you double R30, you get R60. So you're going to have R60 on the outside and R30 on the inside. Total of R90, very well insulated roof. But to make sure you have enough insulation on the outside of the vapor barrier to keep everything on the inside warm enough so that there's no condensing issues, maintaining that 2/3, 1/3 ratio is what we recommend. So 2/3 outside the vapor barrier to 1/3 inside, no moisture issues, no condensation, no mold issues, a nice, dry, warm roof cavity. So to recap the remote system, it's an air vapor barrier all the way from the footer, all the way up the wall and all the way over the roof. One complete sealed bag. Very, very airtight. Probably zero leaks through any of the wall assemblies. All the leakage now is reduced down to window seals and door seals and things like that. Very airtight, very little air infiltration. And the same with the insulation. Insulation is one unbroken plane all the way up the walls, all the way over the ceiling, addressing all of the weaknesses that we talked about before. None of the framing members conduct heat to the outside. The places where the headers displaced insulation, those are addressed. Those have the same insulation as every place else in the building. The corners, all of the potential air leak spots down at the rim joists, where the floor system meets the top of the foundation wall is completely sealed. Where the wall system meets the top of the floor system is completely air sealed. And the insulation doesn't have to stop and start and stop and start. It's one continuous unbroken insulation all the way up over the top. Up at the roof area where the roof meets the top of the wall, there's usually a thermally weak spot with just having solid wood with the double top plates. That conduction is broken and is completely insulated. And where the roof attaches to the top, if you don't have an energy heel, we have a complete depth of insulation all across the roof, even down and around the corner, and then complete wall insulation all the way down. Doing it with the remote system, you can still live in your house, not tear down any sheetrock. If you remove some shingles, you get the peel and stick membrane on, and it's waterproof, it's watertight. You can proceed with the rest of the insulation and redoing the roof and siding without any worry about water damage inside your house. And you can stay living there without worrying about that. Now that we've shown the basics of the system on the model, we're going to go and build one. We're going to build a full-size building addition. And we're going to build it as new construction, but we're going to use some remote retrofit techniques. We're going to build the structure, and then we're going to apply the vapor barrier and the insulation as if it were a remote retrofit process. And we'll cover in that process some of the different products we use other than this peel and stick, how to put them on, how we apply them. We will handle window installation and weatherproofing of the windows. Some windows we'll put flush with the framing, and some we'll pull out flush with the surface of the foam. And we'll also cover the different claddings you can put on the wall and how to handle those: stucco, vinyl, and whatever other siding you want to choose. For the roof, we'll cover fastening the final roofing material, and we'll also cover recreating the soffit so that it doesn't look like a big cube. It'll look like sort of a traditional house with a regular overhang that you can hang a gutter on and that sort of thing. So let's get started. We have a concrete pad poured next to the research center. The pad's 14 by 20, and we're going to add an addition to the side of the building. It's a new structure, a new addition, but some of the aspects of how we're going to construct it are going to mimic a retrofit application. If you're looking for a building manual or a how-to book, one of the best ones is the International Residential Code Book. It not only gives you the information you need to build the structure, but if you build it to the code, you'll pass all your inspections and you'll have a good product in the end. We've built this wall with the header spans, all come from this book. The size of the studs, given the height of our wall, all come from this book. And the spacing of the studs to hold up our snow load and our wind load all come from this book. If you have any questions about your construction project that aren't addressed by the International Residential Code, you should probably call an engineer or structural engineer to have them address the problem for you. The remote wall framing goes quite a lot like regular framing, but there's a few differences that we're going to cover today that help the remote wall go together better. A few differences that for window placement and the framing that you need to do when you're putting all of the insulation on the outside of the building. The wall we have here is framed 16 inches on center, 2x4 wall. And we've used a 2x4 wall because we don't need the depth for insulation. All the insulation is going to be on the outside of the building, and 2x4s are plenty strong enough to hold up the structure we're building here today. It's a little over 11 feet tall on the short end. But since we're putting all the insulation on the exterior of the building, and we want our windows flush with the siding, we have to build a window buck that brings the window out, the thickness of our insulation. And so we're bringing the window buck out. The depth of the insulation, we're using 6 inches of foam, plus the 1/2 inch of sheathing that we're going to be putting on the studs, and plus the 3/4 inch furring strip that we're going to put on top of the foam to hang our vinyl siding on. So to bring the window flange out flush with the siding plane, we've brought this, we've cut this window buck 10 3/4 inches, and that'll bring us out flush with the siding once it's on. We frame the wall with the bucks in there, but to square up the wall, it's easy if you leave these window bucks loose so you can take them out, because otherwise your tape has to go over top of these big bumps in your wall, and it makes squaring up the wall very difficult. So we've built the buck, but we framed around it, and we can pull it out. The other reason to do it that way is you can sheet the wall with your sheeting a lot faster if you pull the buck out. You can either frame the wall with all of your openings 3 inches larger to accommodate the 1.5 inch buck thickness, so that the rough opening for your window sizes is on the inside of the buck, so you have to increase your rough framing opening to accommodate the thickness of the window buck. So the sheeting is going to go a lot faster if we don't have to cut around the window buck. We can just sheet the whole wall, cut out the holes, and throw in the window bucks, nail them in. And then we can put on our drain wrap, put our windows in the wall and stand them up, or we can put them in later. But we'll detail it with rain wrap and put on the insulation and then stand the wall up. So right now we've got the wall all framed. Our wall is over 8 feet tall, so we've got our blocking in there to transfer the shear from our 8 foot tall plywood panels through the wall. I'm going to take the bucks out, pull diagonals on my corners to straighten out the walls, to square up the wall, and then start sheeting it. We've done the same thing with the door opening. We framed it 1.5 inches taller and 3 inches wider to accommodate the 1.5 thick buck extension. And this is a commercial building, so it all has outswing doors on it. So our door and hinges are going to mount to the outboard edge of this. So it's important that we have a strong structure to nail it to. Also, the siding is going to come to the edge of the door, and we're going to use a return flashing to meet up with the jamb extension on the door. With the window bucks out of the way, we can snap a line, straighten the bottom edge, and then pull our diagonals to square our wall. Once you get your wall square, we can nail the structural sheathing on it to keep it square. We'll cut the doors and windows out after we're done sheeting the wall, but we'll mark the holes so we know where to cut. For your shear bracing, for the seismic loads for this area, all you have to do is consult your International Residential Code Book, and it'll give you the size of the fasteners you need to use and the spacing of the fasteners, both around the perimeter, the panel edges, and out in the field. We straightened our bottom plate, squared our wall, nailed the sheathing on. Now we're going to put our window bucks back in and our door bucks back in. We leave our bucks proud by the depth of the foam plus a 3/4 inch furring strip. It's important that your framing is nice and square and that your window bucks are nice and square. It'll make installing your windows much easier. Installing windows and doors this way is known as the exterior method. The exterior method brings the window out to the plane of the siding. Later we will demonstrate other window placement options. It's critical that you decide which placement option you prefer, as it will determine how the rough openings are framed. Please consult the Windows chapter of this video before you start your framing. Sheathing's nailed on, our window bucks are installed, and now we're going to install a Tyvek drain wrap. And the drain wrap is it's made by DuPont. It's very similar to Tyvek. It has a higher or a lower perm rating. It keeps water out, bulk water out, a little bit better than regular Tyvek. And it also has a crinkled surface. And this crinkled surface provides drainage channels behind the foam. If for whatever reason somehow wind-driven rain finds its way behind the foam, it won't get on our plywood sheathing, and it can drain out from behind the foam and down into the dirt. So we're going to put it on shingle style, starting at the bottom, lapping our seams as we go up, and we're going to leave a long tail at the bottom so that we can tab it down over our foundation waterproofing, and we're going to leave a tab at the top that when we put our roof membrane on. We're going to bring the roof membrane down over top of the Tyvek, so everything is layered shingle style, so any bulk water that gets behind the foam can drain right out into the dirt without getting our wood framing or sheathing wet at all. It's a windy day, so it's handy to have a tool like this. This tool pushes out a big plastic washer that it can drive a staple through. And that provides a big pressure surface to keep the Tyvek from tearing over a tiny staple. We're going to leave a generous flap at the corner for going around the corner to overlap on each side of the wall, and we're going to leave a generous flap at the bottom to go out and down over the foundation so that the water drains out and into the dirt and not back in underneath the wall. We're going to leave a generous wrap to come up the side of the frame, and we're going to come over the top of that with a Grace Ice and Water Shield, a Biturethane, or a DuPont Straight Flash, a self-adhering membrane to complete the watertight seal. About 16 inches on the bottom and about 16 inches to go around the corner. To finish off the top of the wall, we're going to lap over the Tyvek below by 8 inches and keep our 16-inch overlap at the corner. And if you notice, all the grooves are going to be vertical when the wall is stood up. Never install the drain wrap with the grooves going horizontal, but we're going to get a good overlap. Any water running down should lap shingle style and continue all the way into the dirt. Remember not to staple too close to the top of a window or a door, because we're going to pull that flap back to put our self-adhering membrane on and underneath so that it laps shingle style so that the water drains off naturally. Cut inside your window buck, however tall your window buck projects from the deck. So ours comes up 6 3/4 inches. So we're going to go in 6 3/4 inches. We already have it wrapped up 6 3/4 on this side. That down. The DuPont Tyvek comes with Tyvek tape. It sticks to the Tyvek very well, and all the seams, both horizontal and vertical, are to be taped with the tape. It provides a more air-resistant barrier. Also, it keeps the wind from getting under it and lifting it, tearing it off your building until you get your siding in or your foam on. Try to do as much of the wall as you can before you stand it up. Working flat is quicker and faster than working vertically. Here we've stood up the walls on each side of the structure. This is the wall we framed earlier, and we had the luxury of putting the drain wrap on while it was on the ground, because it's a new construction project here. If you're retrofitting a house, of course, you're not going to have that luxury, and you're going to have to put the drain wrap on the wall while it's standing up. Simply start at the bottom, leave 10, 12 inches, whatever it takes to lap over your footer foundation, and then just bring it up shingle style, stapling it on, taping the seams to make an airtight barrier, and we're going to staple this on. These snap caps distribute the load of the staple, and they keep it from tearing the drain wrap. And it works really well. We haven't had any blow-offs, and the manufacturer recommends a certain pattern to staple to keep it from blowing off. So we've done that here. If you're going to do a remote roof also, all you have to do is cut your rafter tails off flush with the building. If there isn't blocking in between them, and some older houses don't have it, blocking between the rafters for heel rollover, continue the plywood up, and once you're done flushing the rafter tails with your building, the air barrier and vapor barrier that you're going to use is going to be a peel and stick membrane like this one. The Grace Ice and Water Shield is about 30 mils. And it has sort of a non-skid surface, so it's safer to walk on. But you'll stick that on shingle style, you'll bring it down over to make this air barrier continuous, all the way from the peak, all the way down to the footer. And it's all done lapped shingle style, so any wind-driven rain that gets behind here will drain off, drain down through these grooves, and drain off into the dirt. We're going to do not only a remote wall, we're going to do a remote roof. And that means we're going to run the foam 6 inches thick on the wall, and then we're going to run it 12 inches thick up the roof. On top of that, we'll have 1x4s, and that will provide a surface to screw our metal roofing to. And so the only space between the foam and the metal roofing will be the 3/4 inch of the 1x4. But it's considered a hot roof with no ventilation between the top of the insulation and the roofing material. And our rollover balking is complete. If you are retrofitting a structure, there are a couple of reasons why you'd want to do a remote roof. If there is either no ceiling vapor barrier in your current house, or the vapor barrier is very poor, then putting the vapor barrier on the outside might be the only sure solution to getting an airtight ceiling vapor barrier. And it's also going to be less invasive to the interior. You won't be tearing down sheetrock or disturbing your living area. Another reason might be that if you have a stick-framed roof with no truss space, you can't get a lot of insulation inside the roof, and putting insulation on the roof might be a better solution. Next, we finish attaching the drain wrap on the rest of the walls. Whether you're doing new construction or a retrofit, remember that you're building a very tight envelope. A tight envelope is going to require controlled mechanical ventilation to maintain adequate indoor air quality. Consult with a ventilation specialist to determine the optimal type of ventilation system and the appropriate size of the equipment. This is the top of our foundation wall, and this is the perimeter insulation that is rated for below-grade application. If this was habitable space in the basement, we'd dig all the way down to the footer if it's not already insulated. If it's new construction, you'd put this on before you backfill. We dig all the way down to the footer, put our insulation on, and then wrapping all the way up the footer, we put our water barrier, moisture barrier membrane on. Then we backfill. Then the whole of our foundation is insulated. The wall insulation will come down and land on top of this, and some of it will extend farther down. So our entire structure is encased in foam. For the last part of our air-water barrier, we want to keep water out of our foundation and basement, and bulk water off of the building. We want to flash with bituthane down over the top, shingle style. This creates a nice seal between the wall and the top of the footer, so air cannot infiltrate. After that, we'll bring our Tyvek drain wrap down over top of our counterflashing. If any water ever gets behind our foam for any reason, then it will run down the drain wrap, over the counterflashing, and down into the dirt, and never get our building structure wet.